So.
Okay, so we can start with the public defense of the TFM of the final master work by Maza-Cuello.
So thank you.
Very long name.
So thank you very much. Good morning. My name is Martin Maza-Cuello, and I'm going to present to you some results from my master thesis, Castor crystal under an external flow. In the context of soft matter, we are usually, in a classical sense, talking about a set of many interacting particles that are usually dispersed in some solvent medium. The interest in this type of systems during the last century was flourished from the fact that this type of system are very sensible to both its internal and external forcing or parameters that makes a wide type of different phenomena arise. So for the theoretical description of this type of system, it wasn't necessary to develop new effective interactions among the particles, ranging from the classical Lennard-Joule potential that has these two, is repulsive and attractive at different length scales, to rigid particles, impenetrable particles, and in these last decades, an extension to biological system in different length scales. All these types of phenomena give rise to new form of patterns and new phases that, in both in equilibrium and non-equilibrium scenarios, that provides some surprising phenomena. For instance, in recent years, some interest has been devoted to purely repulsive Brownian particles that have been proven to, in the case of, for instance, in the case of 2 dimensions, and under some special circumstances, may freeze into an stable hexagonal lattice. This type of lattices are called cluster crystals, and as we can see here, this type of structure has not a single particle on its side, but it has this form of clusters of particles on each one of the sides. This is a direct simulation of the Brownian dynamics plus the interaction among the particles. And in this case, for cluster crystals, we're using a soft core repulsive potential such that the particles may overlap between them, and that introduces an energy and a length scale that will be useful later. And for all the simulation, for this and for all the simulations I'm going to show to you, we can define a mean density because we are using a conserved number of particles in this cell. For the simulation, we will use periodic boundary conditions. So this is the particle point of view, and from a continuum description, the Dean-Kawasaki equation has led to interesting results. This equation exactly describes the evolution of the dynamics of the particle density of this set of Brownian particles in the overdamped regime with subjected to a Gaussian noise. Here it is written in dimensionless form using the scales provided by the potential. And the interesting control parameters are d tilde, that is the ratio between the interaction time scale and the diffusive time scale over an interaction region of order r squared, and r measures how many particles are in the homogeneous case inside this interacting region. And for reference, we are going to set this in the interaction time scale of our system, that it will be our reference time scale, to be 0.015. In a work by Delfaux and co-workers, they showed that the growth rate of the Fourier modes on top of the homogeneous case that finally leads to the development of the hexagonal pattern has this particular form. Note that for lambda to be positive, we have to have our potential with negative, that the potential has some negative Fourier modes and that they overcome the diffusive effect. For the generalized exponential model, the potential that we are using, it is sufficient to have an exponent greater than 2, and we are using exponent 3. This will be important later. All these results are from the static, let's say, isolated point of view, both with using only interactions and the Brownian dynamics. Now, in this master thesis, what we have done is to introduce an external forces to to try to control the system and see what happens when we introduce this this external velocity field on the dynamics of the particles. We have used also the Dean-Kawasaki equation plus this new advective term for the analytical discussion that we will show later. And our main control parameters will be d tilde as before, and u tilde, that is the ratio between the interaction time scale and the flow time scale, again in this interaction region. And we will also change the interaction length to see what happens. For reference, our values, our main values, unless otherwise stated, are u equals 3, d equals 0.15, and r equals 0.1 in units of the length of the cell. These two last points of d and r are taken from the reference of Delfaux and co-workers because we want to work in the case when clusters form in the at least in the static case without flow, and we want to see what happens when we apply this external flow. We have used as a base flow this sine flow, that is a toy model used in mixing processes. It's an alternating flow that acts into alternative direction with a sine profile, although we have mainly focused only on the left-hand panel using this shear as a shear flow with a sine profile, although we will say something about the full alternating flow at the end. This flow introduces an intrinsic periodicity in the systems that will be important for the analytical discussion. For reference, it values 0.63. So let's see what happens when we apply this velocity field to the dynamics of these interacting particles. We can see as before that clusters are forming. The flow does not inhibit the formation of clusters, but the hexagonal pattern does not appear. Now we have a new non-equilibrium final steady state that forms channels of clusters that move coherently along the paths given by the velocity field. This non-equilibrium steady state is the same for all the ranges of values that we have considered. Here we see the dynamics for different values of u at different stages. The final steady state is the same, but the short-term dynamics depends slightly on the value of u. Let us recall that u is the ratio between the interaction time scale and the flow time scale, and so when the flow time scale is greater than the interaction time scale, we will first see the clusters form, and the flow will rearrange them into this set of channels. Whereas when the flow time scale is lesser than the interaction time scale, we will first have this formation of channels, and on top of them, clusters will form to get the same type of structure. We can compute which is the periodicity of these channels by computing the two-point distribution function that measures the position of the particles relative to a reference particle. We have performed this average over a temporal series in a single long-run simulation. We compare the case of the static configuration, the hexagonal lattice, and the channels. The channels are formed with a strong value of u, although, as I said before, this configuration in channel does not depend on the value of u, if it is non-zero, of course. The lattice constant from the left panel is seen to be about 1.4, whereas the inter-channel distance, which is the important parameter here, is about 1.25 ROL, and does not depend on the value of u, as I said before. Note that these two values are similar, of the same order, and that will be important later. But now let's turn our attention to what happens when we increase the diffusion. These are non-equilibrium steady state, the final long-time behavior. We see how the clusters widen as d is increased, and after some critical value, we get again the homogeneous configuration. However, we see that the increase in the diffusion does not inhibit the formation of these channels, although here they are diluted. We can see this better with the two-point distribution function. We see here how the channels widen as d is increased. Here we have a non-zero population of particles between channels, because the diffusion allows the particles to jump from one channel to another. And finally, we get the homogeneous case. It is interesting to note that the critical value of the diffusion is around the value of the of the critical value of the diffusion coefficient for the static case, that is about 0.08. And this is something that we will have to explain later in the analytical discussion. Let us see what happens when we change the interaction length that controls the interchannel distance. Here we see the dynamics as before for two values of R. This is half the reference value, that's the cases that we saw earlier. So we see how the clusters form first and the flow slowly reorganizes them into channels, whereas when R is bigger, it's double than the reference value, we have first the formation of channels, and afterwards we have clusters forming on top of them. The interchannel distance can be computed from the two-point distribution function as before, and we see that it follows the same ratio of 1.25. So all this set of results can be qualitatively understood by performing a linear stability analysis of the Dean-Kawasaki equation plus the advective term. Here we present a linearized deterministic version of the equation that's based on a mean field approximation, averaging over the noise realization and with a mean field approximation. And we are going to study what is the growth rate of Fouquet's modes that include explicitly the periodicity imposed by the flow. Inserting this formula into the equation above, we set this, we get this system of linear coupled equations for the coefficient C of n of the Fouquet modes, where the P of n are wave vectors that are displaced by the periodicity of the flow. We are not going to study the whole system of equations, but we focus on the weak coupling approximation, and we are going to study the system only for the three first nodes, n equals 0, n equals 1, and n equals -1, to get this reduced system, homogeneous system of equations. And to get the form of the growth rates, we need to get the characteristic equation of the, solve the characteristic equation of the coefficient matrix. Firstly, we are going to perform another approximation. In this case, noticing that the periodicity in our system is close the periodicities that appear in the static case, we are going to assume that our critical wave vector for the pattern formation is around the critical value of the static case, that is known to be 5, and that is much greater than the referent intrinsic wave vector of the flow. This allows us to perform Taylor expansion of the coefficient A and plus or minus 1, that can be written as A0K plus minus Q. And this term here does not depend explicitly on the flow, and we get these terms that do depend on Q. Plugging all this in the matrix and solving the characteristic equation on this approximation, we get three solutions. The first one here is the same as in the static case. So the hexagonal pattern wants to grow over the homogeneous case, even in the presence of flow. But they are hindered. This hexagonal pattern is hindered by the apparition of these new two solutions. From this expression, we can see that purely transversal modes are static. They have the same formula for the growth rate, although the critical wave vector will be displaced by a factor of Q. But this explains, since they are static, this explains why the distribution of channels in the transversal direction does not depend on time as once they are formed. Whereas purely longitudinal modes are dynamic. They have, again, the same type of periodicities, because the expression for the growth rate for the real part is the same as in the static case, but they are dynamic. They form traveling waves with a velocity that will be proportional to the intensity of the flow, and this introduces the necessary asymmetry to form the channels and clusters on the longitudinal direction following the flow. Note also that since we have the same solutions for the growth rate, and we are using the same interaction potential as in the static case, the critical value of the diffusion coefficient will be the same as before, and this explains the results that we have seen in the simulations. So after we understand what happens in the system, let me briefly discuss what happens when we apply the full alternating chaotic flow to the dynamics of the particles. That's just some brief notes. First of all, what we can see is that when the period is of the order of the interaction length, we are getting the clusters form, but the channels do not have time to form, whereas when the period is sufficiently large, channels form between direction swift. Sorry, I forget to mention that these configurations are just before a direction swift. So after this simulation step, the direction will swift. To know which is the let's say the boundary value of the period such that clusters effectively form between direction swift, we can compute the transversal distribution that is just as the two-point distribution factor that we saw before, but let's say averaged over the longitudinal direction. So plotting h for different value of the period. Here the peaks correspond to the position of the channels inside the cell in the transversal direction, and although we are having always the same modulation as it should be, looking here at the orange points, we see that when the period is of the order of 10 times the interaction time scale, we are effectively getting channels between its direction swift. This may be important for some biological maybe for some chemical or biological process, since here we are, since controlling the period, we are controlling the mixing rate, because on its direction swift, the particles rearrange into new clusters. And this may be important if some process depends on which type of agent, let's say, you have around as a specific particle. So let me sum up our results. First of all, introducing the flow produces these spatiotemporal channels of spatiotemporal pattern, of channels of clusters. The interchannel distance is mainly controlled by the interaction length scale provided by the potential between the particles. Increasing the flow strength promotes the formation of the channels, but increasing the diffusion destroys them as it allows the particles to jump from one channel to another. We have explained qualitatively our results by performing a linear stability analysis of the Dean-Kawasaki equation with the inclusion of the advective term. And finally, we have made some brief notes about what happens when we apply a chaotic flow that allows this rearranging of particles into new clusters that may be important for future research. Here's some of the main references that I have used, and thank you very much for your attention.
Very good. I forgot to say that at respect, you talk for less than 20 minutes, but
just I think
perfectly
okay.
within time. I think you have a little bit more than 15.
Let's put this disk is serious.
Thank you.
Thank you.
So we'll start now.